Hi guys, so welcome to the last of the test corrections video. We're going to do 11 through 18. This is the calculator section of your test, so if you don't already have a calculator out, go ahead and grab one, and we'll start with question 11. So if you remember, and I know the visibility isn't awesome here, but you should have your test in front of you. Question 11 was a limit question, and I've actually done the algebra out right here. So you can take a look at how I did that. Basically, I factored out a GCF. But given that this is a calculator section of the test, you shouldn't be wasting your time with algebra. You should feel confident that you can do that. The right way to do this question is to go into your calculator and start with y equals. And when you get there, clear out whatever you got and type in this equation. Again, I know this screen is a little bit blurry. Do what you can. You've got the test in front of you. Type in that equation. And when you do, you should get something like this. Make sure that you have parentheses around the whole top and the whole bottom. And to evaluate the limit, we're going to use the table feature, which is second graph. But before we go there, we want to make sure that we set up the table correctly. So I just did second window to get the table set. And I want the table to start at the number where I'm evaluating the limit. In this case, it's going to be at 0. And then I want the increments, the delta tables, to be really small. I want to get close to 0. So I'm going to try 0.01 as my increment. You could also do 0.001. And then you do want both of these to be automatic. Now when I go look at my table, I can scroll up and down, and I ask myself the question, what's happening to the y values as my x values move towards 0? In other words, coming down from the top and going up from the bottom. And it looks like on both sides we're approaching negative 0.5, which is why the answer was negative 1/2. Go ahead and try this one for yourself. You can do this one both using algebra and using your graphing calculator. Awesome, so the answer is B, as you saw. And here's kind of the work that I would have done. You can take a look at the algebra, but again, maybe you just did this in your calculator and that would be fine. Okay, moving on to question number 12. This was another question where you could do this in your calculator. Sorry, you can't do this in your calculator because the numbers are getting really big. You're going towards infinity. You can do this just by looking at it. You don't need to do too much algebra. If you remember, there were kind of 3 scenarios. When you're approaching infinity, if the degree on the top and the bottom is the same, then we look at the coefficients. If the degree on the top is largest, the answer is going to be positive or negative infinity. And if the degree on the bottom is largest, then the whole expression is going to approach 0. In this case, the degree on the bottom is 5 and the degree on the top is 4. So we are approaching 0. Try this one. Great, that should have been pretty easy. The answer was A, and I've got kind of an explanation of where I got that from. Pause if you need to think about this for longer, otherwise we'll move on. Question 13 was an implicit differentiation question. And this was actually maybe the most missed question. In fact, we're going to spend a lot of time in class tomorrow. But for now, I expect you to at least understand this example. I'm going to try zooming in a little bit. It might get blurry, but I'll see what I can do to fix this. So the question is asking you about the derivative at a point. And that's kind of your first orientation. That was the light. That's your first hint about how we're going to work this out. We've got an x value, and we know that we need the derivative. But when I look at the equation that we've got, x and y are both on the same side of the equation. So we're going to have to use implicit differentiation. What that looks like is where we take the derivative of both sides. On the right-hand side, the derivative of a number is 0. That's easy. The left-hand side is not quite so easy, so let's look at it piece by piece. First of all, each term we can treat separately. The derivative of 3x squared is 6x. The derivative of negative 2xy requires that I use a product rule, and I usually choose to include the negative as part of my product rule so that I don't have to worry about distributing later. So the way I would think about this is I would think about this as a product rule where u is the function negative 2x and v is the function y. And you really have to remember that y is a function, it's not just a variable. So u dv would be negative 2x times y prime, because that's the derivative of v. And then I would add v du, which is y times the derivative of negative 2x, which is really just negative 2. So I get negative 2y. Finally, the derivative of 3 times y. The constant multiple rule says just keep the 3 the same and take the derivative of y, which is y prime. Next step, we gather all the y prime terms on one side of the equation, subtract or add the others over. We take out a y prime, and there's kind of maybe a step missing here where I took out the GCF, and inside parentheses I had negative 2x plus 3. And then once that was in parentheses, I divided on both sides, and you can see that it ends up right here. Now, we're looking for a numerical derivative, which means I want to plug things in to this equation. I know that x equals 2, but I'm not going to get a number answer until I also plug in a y value. So to get the y value, I have to go back to my original equation, and I use x equals 2, and I plugged this in here for the equation, and then I solved for y. And when I did that, I ended up with a y value of positive 11, which then finally I was able to plug back in over here, and simplifying everything out, I ended up with negative 10 as my derivative value. Now, this is a lot of work. So you want to think about ways that you can take shortcuts since we are in the calculator section of the test. Unfortunately, this all has to be done by hand. There's no way around that. This evaluating could be done in your calculator. Make sure you're careful with parentheses. And some of this solving could be done in your calculator, but there is kind of a bulk of this that you just have to plug through the algebra. All right, how about you try one? Here's a differentiation one for you. Okay, so as you saw, the answer is D. And here's the work that I did. I did it kind of in 3 steps. First, I did my implicit differentiation. This is a y. I know it looks like an x. It's supposed to be just a y right there. This first part was a product rule, so you can see the 2 parts of the product rule, and then the second one was just a constant multiple. From there, I gathered my y primes, took out my GCF, and divided. There's the derivative expression. This is negative 3y squared over 6xy minus 4. Again, I'm sorry, it's blurry here. Before I can figure out numerically what the answer is going to be, I had to figure out what y was, and I did that by plugging in x equals 1 into the original function and just solving for whatever y has to equal. And from there, you plug in, and it pretty clearly comes out to be 3 over 4. If you need more time to think about this, pause the video. Otherwise, we'll move right along. Okay. Question 14 is actually a question from a practice test a long time ago. You may or may not remember it. And this is one where you really want to make strategic use of your calculator. First of all, interpret what the question is talking about. It says, what is the y-intercept of the line that is normal? And then it gives you a function and an x value. So we remember from class today, normal is the opposite reciprocal. And we're looking for the y-intercept, which means I'm probably going to need to write a point-slope equation. So in my head, I'm expecting to come up with something like this, and then convert it around to get something that looks like this, and then that's my answer. Now, using the calculator strategically, the first thing we can do is we can find the slope of a tangent line at x equals negative 1 just by taking the derivative. Put this into y1 and use your calculate feature to get the derivative. When we did that, we got 0.4277 as the tangent line slope. In other words, the derivative at this point. In order to get the slope of the normal line, I grab my calculator and I do negative 1 divided by 0.4277, and it turns out to be negative 2 point something something something. That slope is going to go right here. Now we know the x value. All we need is the y value, and then we can do the conversion. And the y value also comes out of the calculator. Since you already have this expression in y1, just go back to second trace and calculate the value. And it turns out that it's 0.135. When you plug that in right here, the rest is just baby algebra. Distribute and add this term over, and the correct answer was 2.105. Let's try one for you. There are a lot of steps for this one, so have the grit to keep going at it. And the answer was B. And I've got each of the steps written out here. Make sure you know what buttons to push. If you need more time, pause, otherwise we'll move on. The last question on this page, question 15, was really just a definitions question. It said, given that we're talking about the positive half of the graph, this is an asymptote, and really all you had to process is that when we're talking y equals 2, we're talking about a horizontal asymptote. And that's because if you think about a horizontal line, it would cross the y-axis at a particular point. The y values all stay the same. So looking at all of these, this is by definition what a horizontal asymptote is. The x values are going to infinity all the way up here at the positive side, and the answer to the limit is the y value. It stays the same. D in this case is talking about a vertical asymptote, and this vertical asymptotes are written as x equals. So x equals 2 is a vertical asymptote, would be this. F of 2, we don't know anything about what happens at 2. We're not even talking about when x equals 2. And when we have an asymptote, we're not saying that the y value can't equal that number. We're just saying that at the edge of the graph it gets very close to that number. A is also talking about a point, which has nothing to do with this. Here's one for you. Okay, the correct answer is E. That's just another definitional one. If you are looking at the answer here between D and E, this is what this inequality is saying. When they say x is less than or equal to 0, they mean on the left-hand side of the graph, as in the part of the graph where we're going towards negative infinity. And that subtlety is just warning you that sometimes a function can have a different asymptote on either side, and it's important to pay attention to which one it is. This would have been an asymptote at -6 on the right-hand side, whereas this is on the left-hand side, which corresponds to the negative x values. Question 16 was one you should have just done in your calculator. If you put this function into your calculator, again, make sure that you have parentheses here and here. You should see the graph looks something like this, and it has asymptotes at 5 and -1. If you thought that this was 0, well, first of all, there's no option to say both 5 and 0. That's a clue. But you also might need to zoom in and out to see clearly what the asymptote is going to be. Try it with this one. Right, again, this is just a really quick graphing calculator thing. When you put the function in, you get this weird function. It's oscillating and getting really close to 0 on the right-hand side. So we could say as x approaches infinity, the limit of the function equals 0. The y values are approaching 0 on this side, which is a horizontal asymptote at 0. Last one here, question 17. This is a beautiful question. It really tests whether you understand the main concepts from this first semester. In order to check each of these, there are 5 things you need to check. The right-hand limit, the left-hand limit, the actual function value, the right-hand derivative, and the left-hand derivative. If the first 2 equal each other, the limit exists. If the first 3 equal each other, then it's continuous. And if all 3 of these equal each other and the 2 derivatives equal each other, then it's differentiable. Notice how to take the derivative, I don't really have to use the limit definition. I'm just taking the derivative of the right-hand piece and the left-hand piece using normal derivative rules. Now, in this case, the 2 derivatives are different slopes, so this is not differentiable, but it is continuous and the limit does exist. Use that same logic to do this one. All right, As you probably saw, the answer was E. Here's the work if you need to take a look at it.